Great. Yeah, thank you very much for the introduction and the invitation to speak. So the title is Quadratic Twists and Modular L functions, and I'll begin by introducing some notation and just talking about what these basic objects are and the motivation for studying them. So for us, for this talk, little f will be a primitive modular form, weight kappa level n, although neither the weight nor the level is important for us. We'll suppose it's a Hecke eigenform, and in that case, there's an L function associated to f, which has Dirichlet series like this. It's the sum lambda f of n over n to the s, which converges absolutely when the real part of s is greater than 1, and it can be analytically continued to the entire complex plane. For quadratic twists, we're going to let d be a fundamental discriminant. So, and then chi d be I guess this is a Kronecker symbol over here. Okay, so this will denote the primitive quadratic character with conductor d. And then f times chi d is also a Hecke eigenform. So this is the quadratic twist of f. And it has an L function, which also has a Dirichlet series given by this lambda f of n chi d of n over n to the s. Again, convergent, absolutely convergent in the same region, and it can be analytically continued similarly to LSF. So this is related to, well, a number of interesting arithmetic objects. So I'll start this talk by talking about a few concrete sort of connections, and then I'll go on to talk about moments of these L functions. So the first problem I want to talk about is this equidistribution problem from Linux. So if we think about the representation of a number n by the sum of 3 squares, it's well known that n can be represented as x squared plus y squared plus z squared if it's not of a certain form. This is a classical result of Legendre. And when representations do exist, one can ask whether these representations equidistribute on the sphere. So when we can consider x, y, z, and then normalize it, that's on the unit sphere. And then the question is, do they equidistribute, or do they somehow cluster in a weird way? Okay. The picture probably explains it even better. And I guess I should mention I took this picture from a paper of Ellenberg, Michel, and Venkatesh. Linux resolved this using ergodic methods, but subject to some condition that n has to be a quadratic residue modulo some prime. This condition is somewhat unnatural, and Iwaniec was able to remove this condition by considering the Fourier coefficients of half-weight integer modular forms. To be precise, he proved some non-trivial bounds on these Fourier coefficients, and this, through some more standard methods, was able to resolve this issue. These coefficients, so I'm going to let G be a half integer weight cusp form, so primitive. These coefficients we'll call rho G. So the Fourier coefficients of these types of half integer weight forms are related to the L values of these quadratic twists. In particular, the coefficient squared is proportional to the value of the L function at 1/2. So this is Wasper-J's formula. Okay. So for instance, if you wanted to bound these coefficients, you can also bound the L value. So of course, there's more work and far more general questions in this direction that I won't mention. I'll just sort of motivate what we're talking about with the most concrete examples that I can find. Okay. The other important connection is to quadratic twists of the elliptic curves. And here I'll also start with a classical problem, far more classical problem, which is about congruent numbers. So we can call a natural number n congruent if it occurs as the area of a right-angled triangle with rational sides. Okay. This is an example of an impressive congruent number. So it's a triangle with area 157. It's computed by Zagier. It's an illustration from a book by Koblitz, and I downloaded it from Stein's website. So it traveled a long way to be here. Okay. Obviously, you can probably come up with some smaller examples yourself. The connection to elliptic curves comes from a change of variables, if you like. So there's the Pythagorean theorem, the area for a triangle, and then a certain change of variables will lead to this elliptic curve. Y squared is x cubed minus n squared x. And if you analyze this a little bit, you'll see that a number n is congruent if and only if there are solutions to this particular equation here in rational x and y with y non-vanishing. Okay. If y vanishes, you can see that that you don't get anything nice. Okay. So there's a standard change of variables, which will give an equivalent form. And this is the form that I'll mention a little bit later. So this is the ny squared is x cubed minus x. These are quadratic twists of a fixed elliptic curve given by the equation at the bottom. The question of rational points on elliptic curves is certainly not just interesting because it's related to congruent numbers, right? One can ask this question in general. So in general, if I have an elliptic curve E, we can define a similar quadratic twist, which again, probably the most concrete way to write it down would be this. By the modularity theorem, which is now known by the work of Wiles, Taylor, and Boy, Conrad, Diamond, and Taylor, the L function of E, LSE, is equal to the L function of a modular form F, and then the L function attached to the quadratic twist of the elliptic curve E sub D is precisely the type of object that we talked about in the first two slides. Okay, it's this type of quadratic twist of a modular L function. So it's well known that the rational points on the elliptic curve form an abelian group of finite rank, and then the Birch and Swinnerton-Dyer conjecture predicts that this rank R is the same as the order of vanishing of the L function, LSED, at the critical point. I guess I should mention that for me, the critical point will always be s equals a half. That's the normalization I'll use. Okay. So if you're interested in this type of problem, you may well be motivated to be interested in the behavior of these types of L functions near the critical point or at the critical point. Okay, so I'll be talking about moments of L functions. So let me first give you a little bit of background on the statistics of L functions. The heuristic here is that the statistics of families of L functions should match analogous statistics from random matrices. So Katz and Sarnak proved this in many examples of zeta functions and L functions over function fields. So this is also frequently referred to as the Katz-Sarnak philosophy. In the context of moments of L functions, there was great progress from Keating and Snaith, where they had some precise conjectures using a random matrix model. And then there were some more detailed conjectures for general families by Conry, Farmer, Keating, Rubinstein, and Snaith. And then by the separate team, Diakonu, Goldfeld, and Hofstein, using methods from multiple Dirichlet series. The family I'm going to consider is going to be quadratic twists of modular L functions. For simplicity, I'll assume that F is full level, and we'll restrict our attention to fundamental discriminants, which are H times D, where D is odd and square free. So these are also of the form 4 times a even square free number. I'll let this sigma star be a sum over square free integers, and then we want to understand moments of this form. Okay. You don't necessarily need to remember all these conditions. In fact, you can, for the purpose of this talk, just pretend that square free numbers are the same as fundamental discriminants, and it won't really matter too much. So these I'll call the kth moment of this family of quadratic twists. And Keating and Snaith conjectured that these kth moments should be asymptotic to some constant, C depending only on K and F. So K is the sort of the moment and F is the fixed modular form, times X times some power of log X. Okay. So this is not known for too many moments in the sense that it's not been rigorously proved for too many of these moments. So in particular, it's known for the first moment when K is 1 by the work of Murdy, Bump, Friedberg, and Hofstein. So these two first works were really concentrating on the first moment of the derivative of these L functions. This was with some application to Colli-Wagen's work on rank 0, right, of the Birch-Swinnerton-Diamond conjecture. And then there were also some refinements by Ivanets, Stefanicki, Lo Ramakrishnan, Rajivel Sound, and Shen. Okay, so a large number of refinements. The work of Rajivel and Sound, so Max and Sound, did their work mostly motivated by this result down here. So they were interested in the first moment. Well, not really in the first moment, but in a twisted first moment, so like a 1 plus epsilon moment. And they were interested in that because they were able to use that to prove a upper bound of the right order of magnitude for the small moments. So for the kth moment where k is less than or equal to 1. Okay. So the case of the second moment has proven to be more difficult. Heath-Brown's work implies immediately that the second moment is bounded by x to the 1 plus epsilon. The method of Sound, by which I mean the work of Sound on moments of the Riemann zeta function, so upper bound on moments of Riemann zeta function, would give a bound of the form x log x to the 1 plus epsilon. And this was worked out. So Sound worked his out for just the Riemann zeta function. For this family, it was worked out by Milinovich and Turnage-Butterbaugh. And there's a refinement by Harper, which would also lead to the improved result, x log x, which was worked out by Sono. All these results are conditional on the generalized Riemann hypothesis, which I'll always write as GRH. Now, based on similar ideas, and by similar ideas, I mean ideas from here, but applied to bounding shifted moments, Sound and Matt Young proved the conjectured asymptotic, again assuming the generalized Riemann hypothesis. The main result I want to talk about today is the unconditional proof of this. So the result itself is at the second moment, which is the sum over the square of the L values over certain types of fundamental discriminants, is asymptotic to a constant depending on f times x log x. Okay, so that's the result. The constant f can be written down more explicitly. It's going to involve the value of the symmetric square L function at 1, and then some absolutely convergent Euler product. If we include a smooth weight in this sum, then the result can be proven with this error term, so with an x log x to the 1/2 plus epsilon, and then can be improved to x log x to the epsilon with a bit of effort. And that x log x to the epsilon error term is well, it's not quite the limit, but it's basically the limit of the method that I want to describe today. The log x to the epsilon can also be a power of log x. I think maybe log x squared would probably do. Okay. All right. So that's the statement of the main result. Before sort of talking about what goes into the proof, I want to first talk a little bit about some of the other consequences or some of the things that are related to this. Any questions so far, by the way? So I would be happy to answer questions along the way as well, if there are questions.
So I guess it's out of the question to get the main term with the logs and then get a power saving.
Yes, unfortunately, yes. So I think a power saving is beyond what I'm going to talk about today. And but I think if one is clever enough and willing to go through some tricks, one might be able to get like the x order term. But then the error term would just be x over power log x. Yeah.
Of course, I asked that because of proving non-vanishing on a positive.
Yes, absolutely. Yeah. In fact, on the very last slide, I mentioned this as well. Yeah. It would be highly interesting to save a power here. Yeah. Yes. So the methods here that I'll talk about also apply to moments of quadratic Dirichlet functions. So these are, well, it's what they sound like. So these L1 half chi ADs are the values of quadratic Dirichlet functions that I have. We raise them to the power k and then sum them over fundamental discriminants. There is a conjecture from Keating and Snaith as well that these should be asymptotic to some constant depending on k times x times some power of log x. The power of log x is different. The symmetry of the family is supposed to be different. There are some more detailed conjectures from Conry, Farmer, Keating, Rubinstein, Snaith, and also Diacono, Goldfeld, and Hofstein. And these are somewhat interesting in the sense that they disagree. So Diacono, Goldfeld, and Hofstein predict a secondary main term of size x to the 3/4, which is not in the conjectures of CFKRS. Here, there was also quite a bit of work done. So the first and second moments were first computed by Utila, the third moment by Sound, and then there were many refinements with improved error terms. So on the third moment by Diacono, Goldfeld, and Hofstein, the first and third moment by Young, where he did some type of recursive argument to handle the square-free condition. The second moment by Sono, who used the same technique as Young, so he basically adapted the technique of Matt Young to the second moment. And then there is an impressive refinement of the third moment by Diacono and Whitehead. This is a recent result where they actually show that there is a secondary term of order x to the 3/4. So, and thereby showing that this conjecture is maybe a little more accurate than the CFKRS one. The fourth moment was also computed, again assuming the generalized Riemann hypothesis by Shen, who used the same approach as Sound and Matt Young. It's also worth mentioning that in the case of the function field, in the function field case, Alexandra Floria gave the expected asymptotic. Also for the fourth moment, where the base field is fixed and the genus goes to infinity. There, the fourth moment does look like the number field fourth moment. And her technique also gave some low order terms. Our techniques should also extend to give the asymptotic for the fourth moment without GRH, so unconditionally. This is work in progress by Shen and Stuckey, and I think they can also get some lower order terms as well. Okay, so these lower order terms that differ by a power of log. So it's maybe worth mentioning that this is related to rank. In this case, I'll let MD be the order of vanishing of my L function. And then Rx is going to be the sum of all the orders of vanishing. And then it's interesting to try to understand this type of object on average, right? Goldfeld proved that Rx is bounded by X conditionally on GRH. There were a large number of refinements improving the sort of implied constant here, also on GRH. Trivially, the bound for Rx is X log X. And in fact, you can even just look at a single L function and try to apply the very classical argument principle. The work of Pirelli and Pomicala gives this bound, a little o of X log X. And our methods should give the bound X log X, proceeding along the same lines. In related work, or maybe related work in progress, Malasham Kumari emailed me and said that he is trying to adapt these methods to derive asymptotics for moments of derivatives of these L functions, which is related to this as well. To get this type of bound, one also needs to calculate moments of the second derivative. Okay, so questions or comments before I go into the proof. Okay, so I want to talk a little bit about the proof. By that I mean maybe an oversimplified sketch of the proof. First off, maybe I should explain what is the kind of the obstacle here, because this also motivates what we're going to do. So after an application of the approximate functional equation, morally we need to understand sums of this form. This type of sum over n is a replacement for L1/2 f cross chi m. So morally, you can just think of these as the same thing here. And we're studying the second moment, and that's why there's a square. Okay. There are two basic tools in this particular problem. One is Poisson summation, and the other is the functional equation. They do roughly the same thing. For us, they're going to both take some original sum and change it into a dual sum, okay, some other sum. For Poisson summation, I'm going to imagine that it changes a sum over m of length m, where m is over n1, n2, into a dual sum of length n1, n2 over m. Maybe it's worth mentioning that if I square this out up here, it would be a sum over n1, n2, and then m over n1, n2. And this is why we're motivated to look at things of this form. Okay. The functional equation will change this type of sum with this lambda f of n over root n, m over n, into a similar dual sum of length m squared over n. Okay. So both of these are basically of the form conductor over the length of the original sum. And the general rule of thumb is that we will prefer shorter sums. This is not always true. There are some rare cases where you would actually apply this type of tool to get a longer sum. That is, if the structure changes and you can understand the structure on the other side well. But generally, the way that this is used is typically we want shorter sums. Those are easier to understand at the end of the argument. Okay. So assuming that that's the case, neither one of these tools seems to help us understand this type of sum right here. So this is where m is around size x, and n is also around size x. I guess I should mention that little x around size big X, this to me roughly will just mean that there's a constant, I'm making mistakes, so there's a constant big A such that A times big X is less than or equal to little x, is less than or equal to some constant big B times big X. Okay. I'll be kind of liberal with these constants. I won't really mention what they are, but you could write down explicit constants here as well. And this type of sum right here is basically part of the sum that we need to understand, right? Here, m is around size x, n goes up to x. Here, all that's happening is m is around size x, n is around size x. The reason why this neither tool makes us understand or helps us, seems to help us understand this type of sum is because if you believe what I say up here, you'll see that Poisson summation leads to a dual sum of length x over x, so that's still x. And the functional equation also gives you a dual sum of length x. Okay. So neither Poisson summation nor the functional equation seems to help understand this type of sum. It's no surprise that the functional equation doesn't help us because we've actually used the approximate functional equation to get here. So there's no gain in information there. The fact that the Poisson summation doesn't help is really an effect of the fact that we're looking at the second moment. Okay. This type of obstacle is a fairly basic fundamental barrier It occurs in other places, but in other families of L functions, this has turned out to be somewhat easier to deal with. This particular family has proven more tricky. Okay, so I want to concentrate on what do we do with this particular type of sum. Okay. So the idea is some type of truncation argument. So what we want to do is replace the sum n up to x by a shorter sum. And then because the inside sum is shorter, the tools that we mentioned, in particular Poisson summation, will turn out to be useful. Okay. So morally, I'm thinking I want to truncate n at x over a power of log x and not have it go all the way up to x. Okay, so if I want to do that, then I still need to bound the contribution of the sums where n really is around size x, or maybe I should be thinking that n will be between x over log x to the a and x. Okay. So maybe I should pause for questions as well, because I just introduced a bunch of notation. So any questions or doubts? So if you believe what I say, then you see that we're really interested in proving a bound of this form. Okay? As long as I have a bound of this form, I can do some type of dyadic summation, and then I can bound the tail end. So when n is large, when n is between x over power log x and x, it will be bounded by x log x to the epsilon. This is where that error term x log x to the epsilon comes from. And this is good enough because remember the main term is x log x. Okay. So if I'm able to do this, then this reduces the problem to considering the easier problem here. At least I claim that it's easier, and it's at least morally believable that this should be easier based on the tools that we have. Okay. All right. So the main challenge then is to bound this type of sum. So to simplify things, I'm going to think of m as around size x, n around size x. An here for me is going to be the special coefficient, lambda f of n over root n. And we want to show that this is bounded by x. This is the best possible bound up to the implied constant. Okay. There is actually a large sieve bound from Heath-Brown's work, which would imply x times x to the epsilon. But remember that the main term here is some constant times x log x. And the x to the epsilon will overwhelm any power of log x. So it's too large in this case. Okay, if we cannot afford to lose an x to the epsilon. We can afford to lose some power of log x less than 1, however. And this is what Sound and Matt Young did. They didn't explicitly write this down, but their work implicitly proves that this type of sum is bounded by x log x to the 1/2 plus epsilon. Okay. So
when you say that, when you're assuming that generalized Riemann hypothesis for which L functions?
They needed to assume GRH for the L functions that are being studied. And that's it. Yeah. I think it's just the L functions L, S, F cross I, D.
Not directly L functions independently. Okay.
No, I don't think they need to do that. Yeah. So the technique is really only studies a single L function. Yeah.
Okay.
Yeah. Yeah. So they prove this bound by studying a shifted moment. So what they do is they try to bound something like this. So S1 and S2, you can think morally as being small, and then there's a sum over D here. And they're able to save this power of log x, so basically a log x to the 1/2, because they're considering the shifted moment and not a second moment, right? The second moment is x log x. And the shifted moment is genuinely smaller, even when you take absolute values. They lose a power of log x, so they lose this power log x to the 1/2 over the optimal bound because they take absolute values here. Yeah. Is that okay? Any other questions? Okay, so the point here is to try to prove this optimal large sieve type bound, but with these special coefficients. Okay, so we'll sort of exploit the properties of these coefficients. Okay, so I want to give you a sketch of a sketch where I sketch out some rough pictures of what's going to happen. So what we have at the beginning is the sum m around size x, and then sum n. This inner sum is squared, but the important thing is it's around length x as well. And the idea is I don't like this because neither Poisson summation nor the approximate functional equation is useful. So what I want to do is I want to replace this with a longer sum. So in particular, I want the sum over m to be longer. Let's say L times x for some parameter L. You can think of L as some large parameter. And then the sum over n here is still the same. So n is still around size x. Obviously, I need to explain how this happens. So how does that happen? But maybe one thing I'll mention is that we are just doing an upper bound here. Okay, they're not going to be equal to one another. But I will bound a shorter sum by a longer sum, which at least is plausible sounding. And then the idea is that once the sum over m is longer, Poisson summation is actually useful. And you can either know what Poisson summation does, but if you're willing to just believe me, that's also fine. So Poisson summation takes my sum over m, and it makes it shorter. Okay, so originally it was x. If we somehow make it into L times x, Poisson will change it to x over L. And then the sum over n remains the same. Okay, it's still of length x. The next thing to note is that once the sum over m is shorter, the value of m is shorter. So this is a reduction in conductor when you consider the sum over n. And so it makes sense to apply the functional equation. The effect of this is, well, the sum over m doesn't change at all. So it's still going to be x over L. And then the sum over n is now x over L squared. Okay. So, whoops. Yes, that's right. Yeah. Okay. So the thing I want to point out is that this diagram and this diagram are similar. Similar in the most elementary sense, similar in the sense of geometric figures. So in particular, the length of the sum over m is L times the length of the sum over n in both cases. And this suggests that we can iterate the process and continually make our sums over n and sums over m shorter and shorter and shorter. Okay, and if we can do this without loss or too much loss, then surely we would win. Okay. One thing that I'll mention is that, in fact, the argument itself will be phrased as an induction argument, because it's just a little bit cleaner to phrase it as induction. Okay. So that's my sketch of a sketch. I have yet to sort of really explain anything, but this is what you can expect. The first main step is this inflation sort of argument where the sum over m is somehow inflated. It becomes longer than it used to be. So let me first try to explain how this happens. We'll start with a prime, p around size root L, and then in my sum, this quadratic character m over n is basically mp squared over n, simply because p squared over n is typically trivial. It's 1 or 0 depending on whether p divides n or not. Okay. So formally speaking, I do need to include two types of sums. The first term here I claim is illustrative. So I claim that if we understand this, then we understand the second term over here as well. Maybe I'll just make a quick comment that the second term, one can use Hecke multiplicativity to deal with this condition that p divides n. And some type of induction, right? Because you can think of, because once you take out the factor of p, the sum over n will be shorter than it used to be, okay? So I'm going to concentrate just on this thing here. If I do that, what I get, okay, so let me also sum over all the primes in this interval here. So primes of size root L. Okay, so I'll sum over all primes of that form. I'll let P of L be the number of primes in that interval. S, it doesn't really explicitly depend on the prime P. So what I have is just many, many copies of S. So P of L copies of S. And then on the right-hand side, this is my first term that I claim is illustrative over here. Okay, and then all the other stuff I'm going to ignore. And then there's basically a change of variables. I guess if you like, you can also think of this as a embedding. Okay, so all I'm using is that the set mp squared, where m is square free, and m is around size x, p around size root L, this is a subset of the set M, where M is around size XL. As long as I don't worry too much about the constants. Okay. I have forgotten about the square free condition in the second sum, okay, but this will not actually matter for us, as we'll see later. There are two things that are used here. So one is that, well, there's positivity, right? So all the terms that I'm summing are non-negative. They're absolute value squares. So I don't mind, or maybe I should mind, but at the very least, it's still going to be an upper bound, even if I include more of them. And I mentioned this because positivity is not always available. And we'll see an example of that at the end of the talk. And the second thing is that the number of ways of expressing m of this form, so m of size xl in terms of mp squared, is either 0 or 1. So it's basically unique. Okay, so the way that we'll put it is m1 p1 squared is m2 p2 squared. If m1 and m2 are square free, this happens if and only if they're just equal. So p1 is p2 and m1 is m2. Okay, so the number of ways of representing m as mp squared, it's either 0 or 1. Either it's not of that form at all, or there's only one way of doing it. And that means that I don't need to worry about some sort of multiplicity here. Okay. So maybe I should pause for questions again, if there are any. Okay, so this has actually inflated the sum as we wanted, right? So originally M was of size X, now it's of size X times L. So now it's advantageous to execute Poisson over M and start this iterative process that I sketched out. We have discarded the square free condition on M, right? So we started with M square free, we ended up with M not square free, and clearly it's not square free because it's of the form MP squared. We want to include things of that form. This can be very bad for arbitrary coefficients AN. In particular, if you just think of AN as 1, then you might be including many copies of the same sum. And in large sieve type settings, you want to avoid that. You lose primitivity there. Okay, so therefore, we do expect to use the special properties of the coefficients that we have, the lambda f of n over root n. And I've also mentioned here, we've used that p squared over n tends to be trivial, and the representation of m by m prime p squared is unique when m prime is square free. Okay, all right. So the next step is open up the square and then apply Poisson summation, right? If you open up the square, this again becomes n1, n2, some stuff, and then m over n1, n2. And we apply Poisson summation to the sum over m. What we'll get is a main term, or something that you might believe is a main term. This is the diagonal contribution, which simply comes from n1, n2 is a square. So n1 times n2 is a square. You can believe that this is large. This will give you a large term just because the quadratic character will be trivial, right? It will tend to be trivial when n1, n2 is a square. The rest of this is the off-diagonal contribution, so-called just simply because it's not diagonal. And it's going to involve this Gauss-like sum, which first appeared in the work of Sound on non-vanishing, proportion of non-vanishing for quadratic Dirichlet functions. This is a Gauss-like sum. And this Gauss-like sum generically looks like a quadratic character times the square root n1, n2, at least when n1, n2 is square free. Okay, and it tends to vanish when n1, n2 is not square free. So that's what it looks like. If you just replace, well, okay, so maybe I should also mention that the whole point of Poisson summation was that the dual sum would be shorter. So the sum over k here is genuinely shorter. It's going to be x over L. And then the sum we need to look at looks like this. I'm just going to look at the off-diagonal contribution because the diagonal contribution is fairly simple, right? It's just x times L. These two x's cancel. The x actually, if you're really keeping track, came from a factor of square root n1, n2. I'm taking that out, okay? But the point here is that this object looks like a quadratic character chi sub k n1, n2. And so if we did actually just replace that with the quadratic character, we would end up with this sum, which is a sum of the form that looks like the sum we started with. Okay, so there's a sum over k square free, and then a sum over n that looks like what we started with, all squared, except that now k is going to be smaller. It's of size x over L. And because it's smaller, it then makes sense to apply the functional equation of some appropriate L function to also transform the sum over n into something shorter. Okay, and that's the last step in this iterative process that I talked about. Okay, so plenty of notation here. Maybe I'll pause again and invite questions or comments. Okay, So I want to make a structural comment. I've oversimplified some parts, obviously, out of necessity. But there's one part that's worth mentioning, which is that if you really look at this sum at the very end that we're replacing the off-diagonal term with, then you would expect, once you evaluate it, you would actually expect a diagonal contribution, okay? So that's coming from when n1, n2 is a perfect square. And this diagonal contribution you expect to dominate, at least when L is large, and the sum over K is larger than the sum over N. But generically, these Gauss-like sums actually vanish when n1, n2 is square-free, is not square-free, rather. So the same diagonal contribution doesn't exist at all. Okay, so once again, there's no diagonal contribution here, and we're replacing it with something that does have a diagonal contribution, and which can make it genuinely larger in some cases. So this oversimplification is kind of important to point out because this means that this sum here is actually structurally different from this sum. What it means for us is that we need to carefully analyze what prime squares and higher powers do. And it turns out to be a little bit too easy to start losing powers of log unless you're careful here. So I want to make a final comment on what we do when we actually do induction, and the final condition, that the final property of prime squares that we're going to use, okay, which is that there are many prime squares. So what our calculations actually say is that PL, which was the number of primes of size root L, right? So number of primes of size root L. And this was root L over log L, which I'll just think of as being like L to the 1/2 minus epsilon. Okay? So this is less than CLX for some constant C. If we take this, we just assume this is true, and we divide through by L root L over log L, then we would derive that S has to be bounded by L to the 2/3 times X. So L to the 2/3 can be L to the 1/2 plus epsilon, actually. I'm just picking epsilon to be 1/6. Okay. If we use this as our induction hypothesis, what would happen, right? So we would get that, again, these many copies of S is bounded by this diagonal contribution of size X times L. And then this is the off-diagonal contribution. And what's happened is that we transformed the off-diagonal contribution into something that looks like the thing we started with, except with shorter sums. And then we applied the induction hypothesis. Okay, so there was also an induction hypothesis here. Okay, and if you work this out, you'll see that this looks like some constant times XL. And if I divide through by PL, which is of size L to the 1/2 roughly, I'll get that S is bounded by this thing that is my induction hypothesis, and which is what I want to prove, right? L to the 2/3 X times this factor. And the point is that I can make this factor less than or equal to 1 for L sufficiently large. Okay, so C1 and C2 you should expect to be some constants depending only on F. So you can pick L to be a constant, some large constant depending on F. And as long as it's large enough, the savings, this small power saving in L will ensure that your implied constant in the argument doesn't get larger and larger, right? If a constant gets larger, it's not a constant. So the number of primes in this interval length root L being large, this serves to control the loss of constant factors. Okay. Yeah, so that's all that I really want to say about the proof. Are there any questions or comments before I go on to the last slide?
What are you using about the lambda F coefficients to make this work?
Right. So the thing that's really being used, the crucial thing is the functional equation. Yeah, so this thing here. Yeah. So the functional equation is being used to transform this type of sum. And in particular, to make it shorter when it's appropriate. It is also used a little bit at the very beginning with Hecke multiplicativity, but I think that's maybe not as important a place.
And it's not been used in a particularly important way when you're looking at these higher prime powers and things.
Ah, yes, it is used actually. Yeah, I feel like this might be morally less important, but it is used. Yeah. So I end up using the fact that I get symmetric square of functions with the symmetric square with these coefficients, and then I actually end up having to use a zero-free region for the symmetric square of functions. So yes, it is actually used there as well.
Yeah.
Yes. Thank you for that. Yeah, absolutely. Yeah, and I think it's an interesting question as well as to how general a coefficient one can prove this for. Yeah, but maybe we can talk about that later if people are interested. So yeah, on the very last slide, I just want to mention two further problems. One that's rather interesting is this type of problem where f is not g. So we've been talking about the case where f is g, and it's the square of an out function. When f is not g, if one is able to prove something like, this is a constant times x, then that would show that infinitely many of these types of quadratic twists don't vanish. And so this is simultaneous non-vanishing, right, for f and g. It's conceivable that the methods that we're talking about can shed some light on this problem. But as we mentioned at the very beginning, so with this question about the power saving, I think the second problem that I've listed here is truly needs something quite new from what I've described. So here, a short polynomial might be something of length x to the delta for any positive number delta. And one would very much like to do this because putting in a modifier would give a positive proportion non-vanishing for these L functions. In this context, I want to mention as well that I pretended basically the whole way through that Poisson summation is useless unless the dual sum is shorter. This is not necessarily the case. I mean, in the sense that one cannot rigorously prove that this is the case. So in particular, we've seen from the structural comment that the structure of this type of off-diagonal term is actually different from here. So it's possible that it's still useful to apply Poisson summation as long as you have some good way of understanding this thing. Okay. Yeah, and that's the end of my talk. So thank you very much.
Yeah, I have a question.
Okay.
Maybe I missed the beginning. What is known about L1/2? I mean, Sound in his thesis did the square, the cube, and the fourth power of just the Dirichlet L1/2 chi d. How many terms do you have in the logs there? Just the leading term?
So Sound did the cubic moment, and then the fourth moment was unknown unconditionally. So it is known. So the fourth moment is known conditionally, assuming the generalized Riemann hypothesis by the work of Shen. He used the same approach as Sound and Matt Young, and he has just one leading term. So just the largest order term.
So why do your methods not work? Oh, sorry. Why do your methods not work? It's a divisor function. It's that much more complicated.
It does work. Yeah.
So you do get
Yeah, so this is what I was trying to describe here. The methods that I've described does work, or should extend with some work, to unconditionally derive an asymptotic for the fourth moment.
And that'll have an extra logs, right? Extra logs.
Yes, yeah.
I guess I was trying to understand how many logs. You only get the leading log.
So how many logs do you get aside from the leading log, you're saying?
I'm asking what you get, just the leading log power, right?
You get more than just the leading log power.
So what
because,
do you...
Right, okay. So let me try to describe that, because this is still work in progress that doesn't exist yet. So you should expect, I think the main term would be like log to the 10, right? Okay. So I think
I should say this was Sound's second part of his thesis. So I'm glad to see you doing it.
Okay. So he was trying to study the fourth moment for the second part of his thesis?
I asked him to, yeah. Why not?
Oh, I see. Okay. All right. Now I understand that. Okay. Yeah. Yeah. Right. Yeah. So I think fairly naively one can go down to log x to the 9. And this is simply because the truncation error here is a little bit smaller. I think it's like log x to the 8 plus something. I haven't double checked, so don't quote me. But you can certainly get some low order terms.
Sorry, I'm just trying to understand what you're claiming here. So even the first term is not known unconditionally before your work.
Yes, that's right.
Okay.
Yeah. So the first term is not known unconditionally, and now it will be done. Okay. I hope by Shen and Stucky, and they will also get some low order terms as well. Yeah. Although they won't get all of them. Yeah.
Very nice.
Yeah. Well, thank you.
Why are you restricting to 8D?
That's Sound. That goes back to Sound's thesis. I complained about that. And he was just
technical.
It makes life much simpler to write things
because of the root numbers.
Yeah, the root numbers work out right. Yeah. There's no good. I mean, it's just laziness.
It's technical simplicity. It makes it slightly simpler technically. It makes it.
He should have been tougher when he wrote his thesis. Then he would have been forced to consider all the.
But there's not a fundamental root number problem that you're.
No, there's no problem here. You can consider any other form of fundamental discriminant as well.
Okay, yeah, fine.
Yeah, it's purely the most convenient thing.
Right, reciprocity is very clean.
Yeah, sure. I understand why this is nice. I wanted to check that. Sometimes root numbers.
No, it's not. Yeah.
Are more serious.
And
sometimes they're fine.
Right.
Yeah, the restriction to f of full level is also just for technical convenience. If you want to consider, let's say, some fixed level n, then you would also have to be a little more careful about picking this as well. You'd have to restrict the fundamental discriminant to some residue class mod, I don't know, maybe 8n or something like that, to control your root numbers and so on.
Could you maybe just say a couple of words about what goes wrong when you try and look at the fourth moment for the twisted one?
The fourth moment for the twisted one. So instead of a second moment, you want like a power 4 here.
Yeah.
Right. So that's, yeah, that seems far out of reach. And the reason is because in that case, our family, the size of the family would be much, much smaller than the length of the sum here. You could have 4 copies of n, and I mean, morally, it'd be like x to the 4. Yeah. So
how you presented it just seems, this sort of magical trick of inflating the outer sum.
Oh, okay. Yeah, right. So I didn't mention right. So there is a right. Yeah. So okay. So let's pretend for the moment that we are doing the fourth moment. We would have to inflate by a lot, not just a constant, but by a power of x, like x squared, right? We do lose something when we inflate is the problem, because the longer sum, when we inflate it, the longer sum is actually genuinely larger. The sum S is of size x, but this is of size x times L. And we get x times L just from the diagonal term. Okay? So if you inflate by too much, you lose a lot, is the summary of this. I can also divide through by P of L, but P of L is only like root L, right? So we really lose, so we lose a root L in this sort of process, in the process of inflating. In the sense that I'm replacing one thing by something that's truly larger, and I'll lose a factor of root L there. So if L is any power of x, I'm losing too much.
So you mentioned earlier that you might be able to get an error of x log x to the epsilon.
Yeah.
X log x to the 1/2 plus epsilon. How would you, or what choice of L would you require in that case?
Okay. So L is always going to be a constant. And that would lead to this x log x to the epsilon. So the thing that really shows you how you should choose L is here. The bound for our sum is some power of L times x. So the larger L is, the worse this bound is. But you do need L large enough so that we don't sort of start losing constant factors every iterative step, right? Because in just in the estimates themselves, we will see certain constants like C1 and C2 popping out, depending on f. And you don't want to lose some constant depending on those constants. And and this is the part where having many prime squares allows us to control that. Okay, so if you look at this expression that I've written down, you can see if you take L large enough, you can make this small.
Yeah. So what limits you to log x to the 1/2 plus epsilon, at least initially?
No, I would just put L to be some constant depending on f.
Yeah, I mean, or you stated the initial result with an error of x log x to the 1 plus epsilon. If
okay, yeah, let me go back there. Excuse me. Let's see. Where am I? Over here, yeah. So the initial result had no error term. The error term x log x to the 1/2 plus epsilon, this is out of laziness as well. It comes from doing Cauchy shorts and not bothering with actually estimating a certain type of term. The real error is actually just x log x to the epsilon. The log x to the epsilon comes from this log x squared type factor. And just one moment, and I'll explain why you have a loss of log x. This is coming from considering how we found this sum. Okay, so the large sieve sum that doesn't lose anything except for a constant factor. This is when n is over a dyadic interval. But we also need to study this type of sum where n is over an interval of this form. So x over a power of log x up to x. This is longer than a dyadic interval, but the number of dyadic intervals in this interval is log x. And that's why we lose the log x. So so basically, you can't avoid losing the log x. At least not in the truncation argument. And that's where the log x to the epsilon comes from. But L itself is going to be a constant.
Can I ask one more question? So if you Can you write down some refinement of Heath Brown's large sieve result, which takes us into some assumptions about the A of n coefficients and spits out something which saves, which gives you a sort of epsilon plus epsilon?
Yeah, that's an excellent question. Yeah, so Roger asked me the same question when I emailed him. I think so. The quick answer is I don't know because I haven't thought enough about it. I think it'd be very interesting to have a look at it. So the main reason why you would be somewhat hesitant is because we lose primitivity, right? In passing to all numbers from square-free numbers, we lose primitivity. This is bad for arbitrary coefficients. But on the other hand, it's possible not to pass to all numbers. We don't need to do that. We can instead, So here we're passing to all numbers of this size, but we can instead pass to numbers of this size with large square-free part. Okay. And in that case, what should happen in the analysis is that you get kind of two main terms which should cancel out. Okay. So, but I'm not sure what would kind of happen there because Heath Brown's paper is a bit of a monster, and the estimates involved do lose powers of x to the epsilon everywhere. So, yeah. But I think actually that there is some hope that one can have some sort of interesting refinement of Heath Brown's result for moderately arbitrary coefficients. And then that would certainly be interesting.
Are there any more questions? If not, let's unmute ourselves and thank Xiannan again.
All right. Thank you very much.